Hello everyone, welcome to another Learn Extra revision lesson. Now today we're going to be looking at a very important topic in the grade 11 CAPS curriculum, the topic of forces. And I know that many of you have issues with forces, but really they're really exciting and interesting. So let's go and have a look at what we're going to be dealing with today. So as I mentioned, we're looking at forces, and here is what we're going to do. In this session, we're going to first of all define the concept of a force. We're then going to look at the ways that we represent forces, and we're going to spend some time looking at vector diagrams. I know that in grade 10 you were introduced to vectors, and here is an opportunity for us to continue our work with vectors. Vectors will continue all the way through to grade 12, and if you continue with physics later at tertiary level, you will also deal with vectors. And so make sure that you've got the principles and the basics in place. The next thing we're going to do is we're going to solve problems when two or more forces act on an object. Are acting on an object. We're also going to identify different forces, including friction and something called the normal force. So in this session, those are the key ideas that we're going to be focusing on, and I hope that you'll follow with me. Make sure that you follow with the X sheets and work through the problems as we do them. So let's get going. Now, the first thing that I'm going to ask is, what is a force? When we look at the idea of a force, it's something that is intuitive, something that we understand, we use in everyday life. It's even been used in some movies, and I won't go into quoting about the force and what it does for you. But a force in everyday life, it's either a push or a pull. There is some interaction between an object and another object in which there is this action being observed on it or exerted on it. Now, it's very important that you need to know that a push or pull doesn't necessarily mean that the object is going to start moving. We can apply a push or a pull on objects and they might stay perfectly stationary. Doesn't mean there has to be motion. The relationship between motion and forces is something that we'll examine in another session when we deal with Newton's laws. So for the moment, our idea of push or pull is sufficient. What we need to understand about forces then is that because they have, we can describe them as push or pulls, they have size, which in physics we refer to as magnitude, and I'll just put that in brackets. But what's also important is direction. Now, you can imagine that if you're standing on the edge of a cliff and somebody exerts a force on you, it's very important to know which direction that force is acting on. Because in one direction it could mean that you go for a big swim. In another direction it could mean it saves you from a dangerous situation. So direction is really important. So because of that, the size and direction, we say that force is a type of a vector quantity. It's a physical quantity that we can describe using a vector. Now, how do we represent that? Well, remember that all vectors can be represented with a little arrow. So we can say, we can put an arrow on it and represent the length of this arrow as being the size. So from there through to there, that's telling you the size. Whereas the arrow direction, the direction it's pointing in, is telling you something about the direction. Also, just to notice that in terms of this, we call the end of the vector, the force vector, that has got the arrow, we call that the head, and the part that hasn't got the arrow, we call that the tail. So we use that sort of notation to represent a force. And we can obviously label it, and that's also very important, and we can call it the particular force. So we sometimes use the capital F for force, and we could put a subscript to describe it as saying it's a pull, or it's a push, or it's an applied force, or it could be the force of friction, which we will deal with a little later. Now, And there's another term that's really important, and it's an idea that I want you to get in your head right from the beginning when we're talking about forces, is that we have these forces that are collinear. Let's have a look at what this means. So collinear simply means that they're in a straight line. So it's in one line, or one dimension. So if we take a look at these three forces that have been shown here, this one, the orange one, is parallel to the green and yellow one. And I can actually recognize that the green and yellow one are in one line, but this one is parallel. But I can move it because it's parallel and put them in that order. Notice we can put them together as the head of this one, the head of the green one, next to the tail of the yellow one. And in this way, we can get a picture of what the overall effect of these three collinear forces would be. So it's, even though they're parallel to each other, we can draw them so that they're in one line. Very important that you understand that. And we're going to use that idea quite a few times. It's important also, another term that we will use when we add these sort of vectors together, whether they're going horizontally or left to, or up or down, we would need to give the direction. So this would be a certain force, and we would say to the left, or we could use some other compass direction. We could use compass direction points, compass points, to give the direction. We could also use something called bearing, where bearing is used as an angle. So where north is 0 or 360, east is 90, and south is 180, and west is 270. So we can use bearing as well. We can also use, in some cases, angle. Now, angle is different to bearing. So if we have a horizontal line, we could say we want the force that is exerted at an angle of 30 degrees to the horizontal. So there's a reference point, the ground being the green arrow and the yellow line representing a force vector that's acting at 30 degrees to the horizontal. So those are all important ideas. When we add up these forces that are in one line, we can find the overall effect. The overall effect. And we call the overall effect, or the sum of the vectors of the forces, we call that the resultant. We even sometimes say it's the resultant force. Understand something. It's not a new force. It's just the overall effect of the combination of all the individual vectors. So in this case, if I were to say, well, what's the resultant? I could write it down like this and say, well, instead of putting the orange, yellow, and green one together, I can replace them by one single vector, which is the pink one, and that would be the resultant of those three forces. So this one we'd write down as F resultant. Another notation is to say F net. It's the overall effect of adding those together. Right, so remember, whenever we have vectors and forces, vectors are forces, we must show magnitude and direction, and we must give that very carefully. There are many conventions for doing that. I've just named a few, and we need to take note of those. We will come back to that, I'm sure, in later sessions. So let's now move on and talk about a very important idea of free body diagrams. You say, what is a free body diagram? Well, here's a little sketch where I have a box on a smooth surface. So this happens to be a smooth, and for the moment, let's just say that it's a smooth horizontal surface. We're not saying it's frictionless, but what we're saying is we're pulling on the box using a rope, and the force in a rope is often called, this force is called tension. Another name for the force in a rope, and we can either give it a capital T or we can write it as F tension. Those two are all notations. Now, what other forces are acting on the box? Well, you need to think about this a little bit. We all know that there is a force that keeps us on the earth. That's the force due to the gravitational field that is around the earth. Because the earth has a big mass, we have mass, there is an attraction between the bodies, our body and the earth, and that pulls us downwards towards the earth, but we're pulling the earth backwards to us. So there is this pair of forces which we will deal with again in a later session. But for the moment, what I want you to understand is that there is a downward force, which I'm going to indicate as the force due to gravity. Force of the earth pulling on the box. This is equal to the mass of the box times the acceleration due to gravity on Earth, because we're dealing with Earth, and that little g there is equal to 9,8 meters per second per second. Okay, it's an acceleration, because we know if we drop anything in the area close to the Earth's surface, it will fall. We're very familiar with that. You drop something, it will fall, and it will accelerate downwards at 9,8 meters per second. That's the size of the acceleration due to gravity. The size of the force that's pulling that object downward is its mass, measured in kilograms, times its acceleration. So we need to recognize that very carefully. Now, what else can we suggest? Well, if the box is acting on the surface downwards, if I push down on something with my hand pushing down on my other hand, what do I feel? You try it. You push down with your one hand. Well, I'm sure you'll feel that the hand at the bottom starts to exert an upward force in opposition. So yes, there is. There's another force that's acting opposite to the force downwards. This opposite force, I'm going to just draw it in pink, so we've got it very clearly, is the same size as the force due to gravity. It acts at 90 degrees to the surface. And so for that reason, we call it the normal force. It is exactly the same size as the force due to gravity, and the important thing is that it is at 90 degrees to the surface. Right. So if we have another look at this box and a rope being pulled, we said it was a smooth surface, horizontal, but there could be something that opposes. We know if you pull the box, sometimes there's something that resists, a certain sense of resistance. You try and push something or pull it, you're going to get something that pushes back. And that force we call friction. Now, we will deal with these in more detail towards the end of the session, but I'm just going to put it in over here like this and say, here is a diagram that represents all the forces acting on the box. So that's what we filled in. We've got all the forces, we filled them in, we've identified them. There's the force of tension, which we're going to call the force applied, another word for it, which is in the rope. So we could even say force of the rope on the box. The other force is the force of gravity, or due to gravity. We're going to say this is the force of the earth on the box. You can also say that there's a normal force. The normal force is the force of the surface on the box. And notice that this one is up, and the force of gravity is down. And the last one that we mentioned was the force of friction. So this is the thing that the force that opposes motion. So if you start to pull on something, it's going to oppose it, doesn't want to let you move it. So if we want to, we could draw these fancy diagrams all the time with labels and all that sort of thing, but we want to be a little bit more scientific. That's why we have what is called a free body diagram. Takes out all the unnecessary detail. It represents the object that there are forces on as a dot, and we fill in the rest of the diagram. So I'm going to draw that just very quickly over here. I'm going to just change my pen color. I'm going to say there's the free body. That represents the box. What I'm going to do next is I'm going to say, let's put in the force of friction. And in this case, I'm going to make the frictional force smaller than the force that is applied with the tension of the rope. So over here, this is the force applied. And I'm putting in brackets here, tension, just so that you remember that word. And then the last two that I want to take note of here is the normal force, which is that one, F normal. Remember, it's the force of the surface on the object, and in exactly the opposite direction, acting downwards, we get the force due to gravity, the force of the earth on the object, and these two are equal. Now, if we've got forces in opposite direction and they're equal in magnitude, then the resultant of those two forces, if we add them together, is going to be 0. If we put them head to tail, you'll see that. So what we're left with here is a situation where this force and this force kind of cancel each other out. And what we're left with is only having to worry about the frictional force and the applied force. And in this diagram, we can say the force applied is greater than the force of friction. And so we would be able to see that there is going to be a resultant. And the resultant force is going to be adding those two vectors together, and it's going to be causing that there's a force on the box that moves to the right. So make sure that you've got that. We can predict from this diagram that the resultant force is going to be, we won't put it on, but just to explain, that's a free body diagram, but in our thinking, we're going to say there is a resultant force that acts to the right. Please make sure that you don't include the resultant in a free body diagram, but it needs to be in your thinking. Okay, I think we can go on to our next thing, and that is to apply some of our knowledge that we've just spoken about. Let's apply it to a question, an example question. So question number 1 says the following. It says, we have a young boy that has a mass of 58 kilograms, and he uses a rope to climb a wall. When he reaches a height of 8.5 meters above the ground, he stops to take a rest. He is still pulling on the rope, so there's a force with his hands, but at the same time, his feet are pushing against the wall. First of all, we're asked to identify all the forces acting on the boy and to draw a free body diagram. So, if I want to show you here, my sketching isn't that great, but we'll try and get it done. If we've got the wall over here, and we're going to say, here is a young chap, and he's got his feet over there, and he's got his hands over there, and he's sitting over there, something like that. We've got the rope coming at an angle, and at that point, that's the picture that we can draw. Now let's identify the forces. What forces can you see? Well, there's definitely a force of tension in the rope, and that rope is holding him, so I guess the direction of that rope must be pulling him upwards. So we're going to say this is a force of tension. What else? Well, we know that he's pushing with his foot against the wall, so there must be a force in that direction, because he's pushing away. The wall, he's pushing against the wall, the wall's pushing back at him, so acting on him is the wall pushing him away through his foot. And then what about the last force? So what we recognize here is that this is the force of the wall on the boy through his foot. It's pushing him away. What else do we recognize? Well, we mustn't forget, very important, what else is always acting on the object? Yes, you got it. We know that he's not in space, he's not floating in the moon, but there is the force of the earth pulling downwards on him. And so in which direction does the force of gravity act? It always acts directly downwards. So Fg, we're going to write it like that. And so that might be a description of the forces that are taking place on the body. And we've identified them. But it's not a free body diagram. What we've got to do to get a free body diagram is to put the center of the boy's mass as a dot. We're going to say that dot represents where all the forces are acting on. And the first thing we're going to do is we're going to draw in the vertical force. We're going to say, let's draw the force downwards. Now, we're going to draw that one downwards. We're going to then say there is another force that is the force of the rope that's pushing up like that. Now, in this case, we're going to write that as Ft. And the final thing is that we've got a third force, and perhaps I haven't drawn it terribly accurately in terms of the direction, but we could fill it in and say that it's acting, pushing the boy away from the wall. Now, what you can see, if these two forces, if this force and this force, the force of gravity, acted just on the boy, they would kind of pull the boy in a particular direction. They would pull the boy in some direction like that. But what we notice is that he's balancing. He's taking a rest. And so there is the force that's pushing him away from the wall that counteracts that. And so what we're going to say is there's this force, and I want to keep it in purple, so let me just change the pen. This force is the force of the wall. Now, that's quite interesting. If we add all these forces together and we arrange them head to tail, like we did with the collinear ones, notice these aren't in the same direction, but we can apply the same principle, then we're going to see something really interesting. Because this object, this boy, is taking a rest, we would say that he's in a state of equilibrium. There is no resultant force on him. And so when we take these forces, what we can do is we can actually redraw them into a triangle. We redraw them into a triangle with the force downwards, Fg, and we're going to draw the force of tension, the force of the rope, and we're then going to draw the next one, which is the force of the wall on the boy. And what do you notice? We notice that there is a closed triangle. Whenever you join the forces, and I haven't done it very accurately, but you can do it accurately, you can be asked to do it very accurately, measuring angles and all that sort of thing. But what we're going to find is that when we've got a closed triangle, then there we can make a conclusion. And the conclusion is that there is no resultant. It also means that this object is at rest, or we could even say it's in equilibrium. Okay, very important to recognize that there's no resultant, it's in equilibrium. One of the options, in this case, the option was that it's at rest. It's not the only thing, we'll learn a bit more about that, but this object is in equilibrium, it's at rest, closed triangle. Bear that in mind. Make sure that you can do it. Have a look around you and look at different objects so that you can begin to identify, is there a resultant or is there no resultant? That's really important. Have a look in your everyday life situation and I'm sure you'll come to different conclusions as well. Okay, you know what? I think that we've done quite a bit of work so far. It's time to take a short break, take a stretch, look at your notes, make sure you're up to date, and we'll be back straight after this. Right, welcome back everyone. Let's move on to our next big idea. what we've just seen is how we can add forces together or represent them in a diagram. We want to take a little bit more time dealing with the addition of forces. So let's go and have a look. There are different ways of doing it. It's always good when you're doing addition of forces to draw a diagram, just like the one we've drawn before. But then there are two methods for solving the problems. The one is to draw a scale diagram. Now, we're not going to spend too much time on that, but the type of thing that you would do is you would say, for example, that let's represent 1 Newton and let's make that represent 1 centimeter. And so you could get a diagram where you would say the scale is 1:1, where newtons is the force, this would be the force, and this is the distance or the magnitude or the size that you're going to draw in centimeters. We would need to be very careful using a ruler and a protractor to measure the angles accurately, and in most cases you can do this. Now, what I encourage learners to do is, even if they're drawing a scale diagram, draw a sketch first. Wherever you've got a force problem or a vector problem, where we will do vectors later in grade 12, not just dealing with forces, you must draw a sketch. Doesn't have to be a scale diagram. Scale diagram can give you some measure of accuracy, but it's not the most accurate way of doing it. It's also very important to remember that when you're reading on your ruler, to keep your eye in line with the ruler, don't develop an error of parallax where you're looking from one side or from the other side. Make sure your eye is over the ruler and in line with where you've got it. The bigger your scale, or the more concentrated your scale, the more your error can be. So be very careful about choosing the correct scale. So it's often better to draw your diagrams as big as possible. When you draw them very small, you can make mistakes and there can be errors involved. But I want to move on to the bicalculation type of problem. So let's run through a typical example. What we're going to say is that you're going to use Pythagoras and you're going to use trigonometry. And in general, we're going to start with two forces that are at 90 degrees. So we're going to say, let's start with two forces at 90 degrees. And where are we going to go with this? We're going to say, let's have that force being a certain number of newtons, and let's have the other force, draw it in a green line over there, like that, being the horizontal. This doesn't have to be vertical and horizontal. It could be a top view where this one is force number 2 and it's acting towards the east, and this one is force 1 and it's going north. Okay, so how are we going to deal with this? Notice that these two are touching each other tail to tail. So that's the first thing that you need to recognize. We can't ever deal with forces in addition when they are tail to tail. They must be head to tail. Now remember, I gave you a little hint a little while ago when I said when we were dealing with collinear vectors, forces. I said to you that they could all be in the same line or they could be parallel. We can move a force that is parallel to another one and we move it so that it is in the same line. So I'm going to apply that idea here. I'm going to say to myself, instead of dealing with this situation where this force is lying like that and it's tail to tail, I want it to be head to tail. I'm going to move it parallel to itself. And I'm now going to position it in a position where it is acting not tail to tail. It was tail to tail, and I've changed that now. I'm going to cross out the tail to tail. Don't want that. Cross that out. I've noticed I've now placed it so it's head to tail. And they're at 90 degrees. So what's coming on here to me, what makes sense to me, is that I can actually complete a right-angled triangle. This force will be the resultant. So that's your net force or your resultant. And so there is something that is a very useful technique. As soon as we know that's a 90-degree triangle and we've got a resultant that we want to find, what are we going to do? We're going to remember Pythagoras' law, which says the resultant, which is the hypotenuse in this case, and we're going to square it, is equal to the sum of the other two. So it's equal to f1 squared plus f2 squared. So we take the square and we take the force, square it, add it to the other force, and then we'll be able to find the resultant by taking the square root. Now, that will cater for dealing with the size or the magnitude of the force. But what about the direction? We're not sure how to find the angle. Well, no, it's not that difficult. We have something called trigonometry to help us. And I know that you're very familiar with this, dealing with angles in a triangle. We call that angle theta, and we want to find it. Well, look what's happening here. The angle is like the eye, and it looks across here and sees, on the opposite side, I've got F1. So let me just move F1 into position, and there we go. That is opposite. Want to note that? This is opposite. And what is next to? It's F2. So that is adjacent. I don't know the resultant. If I could have worked it out from there, I could use it. But I like to use the things that I'm given. I was given F1 and F2. And I know that opposite over adjacent is a trig ratio. And I can write it as follows. Tan theta is equal to opposite over adjacent, which means that I can do F1 over F2. So I can simply take the ratio F1 divided by F2, and I've got tan theta. I use my calculator, second function, and I find theta. In this case, remember I said to you that F2 was in the easterly direction. So what I'm going to do is I'm going to subtract theta from 90, and I will get the bearing. I'll be able to say what the resultant is using this method. Now, it's all very well talking in general terms and showing you the method like that, but let's do an example. So let's go to our next page. And so exactly here, we've got an example. And it says the following. It says, two boys attach a rope to a box. We're dealing with lots of boxes along a smooth horizontal surface. We're going to ignore friction for the moment. One boy exerts a force of 8 newtons on the rope, and the other exerts a force of 6 newtons at 90 degrees to the other force using his rope. And what it says is find the resultant of the two forces. Now, when it says find the resultant, you must remember you've got to find both this magnitude, which is, and direction. Now, I don't know about you, but I'm a little not so sure about this, what all these words mean. So I like to draw a picture. I'm going to see if we can find a box and put the box in. So there's my box. And what I'm recognizing doesn't tell me in which direction it is, whether it's north, south, east, or west, but it tells me that if I've got the one force acting in that direction, then the other force, and I just want to make this a little bit bigger, so let's just do that so we can see it, and let's put that one in as the first one, and we're going to call that 8 newtons. And let's have the second force in a different color. Let's choose the pink one, and we know that that's not going to be as big, so I'm going to make it a little bit smaller. I'll still make it fatter so you can see. So let's just do that change quickly. Make it fatter. And that looks about right. Let's just make it a little bit smaller so that we can see that this one represents 6 newtons. Notice that these are lying in a position where they're acting on the box and they're acting tail to tail. So if we were to draw a free body diagram, we can see they're going from one point, and they're both acting in the same direction, from that one point away. They're not acting head to head. We've got to do something to make sure that the vectors are drawn head to tail. So what I'm going to do, what I did last time, I'm going to do exactly the same thing, but this time I'm going to just copy. I'm going to copy this vector, and I'm going to say, let's paste it. I want to put it in a parallel position. It's now in parallel to where it was. This one has moved. It's disappeared. We're not going to worry about it anymore. So I'm going to throw it away, but I just want you to see that they are parallel. I'm going to take this one and throw it away, ignoring it. Where is the resultant going to be? Well, the resultant is going to start at that position, and it's going to end up at that position there. Just put it in like that, and let's just make that a little bit clearer by making the line fatter and also putting an arrow head on the end. And I'm sure that you can see now that that makes a lot of sense. We've got two vectors. They're acting at 90 degrees. We were told that this angle here is 90 degrees. Remember that little square there represents the notation for 90 degrees. And we want to now work out what is the resultant force. Not going to be too difficult to do that. We want F resultant. We're going to apply Pythagoras, and I just want to label that F resultant, or F net, as it's sometimes called. Means exactly the same thing. So we're going to say F net squared is equal to F1 squared plus F2 squared. And let's do the substitution. We're going to say F1 was 8 newtons. We must square it. F2 was 6 newtons. We must square that. You can use a calculator to do this. We're going to say 8 squared is 64, and 6 squared is 36. We add those two together, and we get an answer of 100. But notice something, that this is still squared. Now, I wish I had a rand for every time a student forgot to square. You know what? I've even done it. I've done it when I've been presenting as well. So make sure that when you're wanting to square something, you see square, make sure that you don't forget that you've squared it. I don't want F net squared. I want F net. How are we going to find it? We're going to take the square root. And so we're going to say, therefore, F net is going to be the square root. And in this case, we're looking only at the positive square root because we don't really want negative numbers here. And we're going to say the positive square root of 100 is 10. 10 newtons. So there we've got it. We know that F net is 10 newtons, and it's acting in that direction to complete the triangle. Now, please don't think that this triangle is in equilibrium. It's not. You can see that very carefully if you take a look at the direction of the arrows. Notice here, where the resultant is, there you've got arrows head to head. That means that you've got a resultant. If you see all the vectors are like that, head to tail, all head to tail, and it's a closed triangle, then the resultant is equal to 0 newtons. So here we've got a resultant, here the resultant is 0 newtons. Be very careful about that. Now, we haven't finished, because what we need to do is we need to find this angle theta. We need to find the angle of the resultant. How are we going to do it? Let's make sure 6 is the opposite and 8 is the adjacent. So now I'm going to need my calculator. I'm going to say tan of theta is equal to the opposite, which was 6, divided by 8. And I now need to use my calculator, which I'm going to call up over here. And so let's do it. We're going to say 6 divided by 8 gives me an answer of 3/4. I want that in decimals, and I'm now going to use my tan function. I'm going to say, I want the second function. I'm going to go shift, tan, and I'm going to take the answer from the previous part of the problem. I'm going to say equals. And from that, I can now read on my calculator that the answer of theta is equal to, pick it up, 36,87 degrees, rounding to 2 decimal places. 36,87 degrees. 36,87 degrees. So my full answer is that the net force is equal to 10 newtons acting at an angle of 36,87 degrees to which vector, which force? Well, there it is. You can see it's acting at that angle to the 8 Newton force, to the first boy's force, to the 8 Newton force. And there we've got it. Straightforward as that. There's your method for solving vectors, two vectors that are perpendicular to each other. Now you might say to me, but hold on, I know that it can't get that much more difficult, but that almost seems too easy. What happens if we've got more vectors? Well, there's one thing that I need to teach you, a skill that I need to remind you about that is going to help you deal with other vectors. When we've got more than 2, you can get up to 4 acting on one body, but the method that we're going to use is very straightforward. In this case, what we've done is we've taken 2 vectors and we found a resultant. We're now going to do the opposite process. We're going to take one vector and we're going to divide it into 2 parts that make up the right-angled triangle. We say we are resolving a vector into its perpendicular components. Have a look at what I mean. So here's another diagram, and it's our familiar situation of a rope and a box, but this time the rope isn't being pulled horizontally. The rope is being pulled at an angle, and I'm going to call that angle theta. It's an angle theta to the horizontal. So in this case, we can draw those in this vector sketch here. What I'm going to say to you is that this part, which is the actual force, can be broken apart into a vertical component plus a horizontal component. Now, say to me, how do you know that? Well, it's not too difficult. Have a look here. If I take this particular line and I move it parallel and I put it over there, can you see it forms a 90-degree triangle? So very clear that we can resolve these into components. So how are we going to actually work them out? Well, fortunately, we are given only one value, but you have to be given the angle as well. So when you're given the starting position, you are going to be given the size, the magnitude, so you'll know the size, and you'll know the direction. So it's not too much to see that in a right-angled triangle where we have one side and the angle, and it's a right angle, we can use our trig ratios. Look here, this is the hypotenuse. This is the adjacent to the angle. This is the opposite. So what we can do is we know that there are 3 trig ratios that we use commonly. There are 6 in total. But we can use sine theta in this case, which is opposite over hypotenuse, and cos theta, which is adjacent over hypotenuse. Now, what we want is we want to find the adjacent. What we want to find is the opposite. So if we just multiply by hypotenuse on both sides, we'll get that. And so that's exactly the formula that we're going to use. We're going to say the vertical component is always equal to the force times sine theta. Then the horizontal component is always going to be the force times the cosine of theta. Hope that makes sense. Take a moment to breathe. This is very doable. And it's really interesting when we start to do problems that we can take any vector, any force, and break it down into its horizontal and vertical parts, parts that are at 90 degrees to each other. Let's see what our question entails. Question 3 says, a crane is used to lift a load with a mass of 525 kilograms from the ground onto the top of a building. The tension in the cable, so tension is a force in the cable of the crane, is 5,500 newtons. It acts at an angle of 45 degrees to the vertical. It tells us that a construction worker guides the load by pulling it using a strong rope. The rope makes an angle of 30 degrees to the horizontal. The tension in this rope is 2,400 newtons. There they give us the diagram. So let's just fill in some detail here. The first thing that we're going to do is the tension in the rope was 2,400 newtons. And you can see it's 30 degrees below the horizontal, whereas the cable had a tension of 5,500 at 5,500 newtons, and that's at an angle of 45 degrees to the vertical. But there's another piece of information that we're given. We're given the mass. And we know that there is a force acting on the load. That's the force of gravity, Fg, where Fg is equal to the mass times the acceleration due to gravity. So how do we go about solving this problem? They say to us that we have to calculate the resultant of these forces acting on the box, on the load. So the first thing that I like to do is I like to draw a free body diagram. It's not required in this example, but it really is useful for us to do it so we can set everything up. So we're going to say, let's draw a dot to represent our load. So there's the dot, and we now recognize that we've got a force downwards. That force vertically downwards is Fg. We'll calculate that by using its mass times the acceleration due to gravity. Let's just get that done right away. So we've got it. The mass was 525 kilograms. And we're going to multiply that by 9,8. Using the calculator, we say 525 multiplied by 9,8, and we get an answer of 5145. So 5145 newtons, and we must recognize it's down. What else are we told? Let's fill in the other forces. The force of 4,200 at 30 degrees to the horizontal, so let's fill that one in. We recognize that it's going to be an arrow in that direction, 2,400 newtons, and the angle here is 30 degrees. And the final force that we've got in this free body diagram is this one, 5,500 newtons, and it's at 45 degrees to the vertical. But 45 degrees to the vertical is the same as 45 degrees to the horizontal. So I'm going to put that one up there, and I'm saying that it is pulling away from the object, and it's at 45 degrees, and it is a force of 5,500 newtons. So there's our force diagram, our free body diagram. We've got all the bits and pieces together. Have a careful look at it. We recognize that these forces are acting on one object, the load. So they're all tail to tail. We need to find a way that we can resolve them so we can draw a nice diagram where we can find the resultant. The easiest way to do that is to take each of the individual forces and find their components. the vertical component and the horizontal component. And then we'll add them together to get one vertical and one horizontal, and then we'll find the resultant. That's the process we're going to go through. So let's see exactly where we're going here. So I want to first of all start with this force, the tension in the cable. So there we go. And I want to find what its horizontal and its vertical components are. Remember in the previous section we said that the vertical component is equal to the force times sine theta, and the horizontal component is equal to the force times cos of the angle. So let's substitute in and let's get some answers working. I just want to give myself some space. So I'm going to move that one down a little bit so I've got that first of all. We're dealing with this force, which is the 5,500. 5,500. Let's put it in. 5,500 times sine of 45. Get the old calculator up, and you can see 5,500 times sine 45, close the brackets, and we'll get an equal sign there, and we're told that it's 3,889,08. We can round it off to 0.9. That would be correct to 2 decimal places. 3,889,09. Newtons. Notice that's the vertical component. But because it's sine theta, we should recognize in any triangle with 45 degrees, the horizontal and the vertical will be the same. You can check it on your calculator, but I'm going to write it down directly. So if you try it, you'll do 5500 times cos of 45, which is the same as sine 45, so the answer has to be the same, 3,889,09 newtons. Important, we need to put the directions in, recognize that this one is up and this one is to the left. Now, let's look at the next one, which is this value here, the horizontal and vertical component of the rope. Now, if we take a look at the rope, and I'm going to work in a different color, we're doing exactly the same calculation. We're going to say vertical component is equal to F times sine theta, and we're going to then do the horizontal component, which is going to be F times cos of the angle theta. In this case, the angle, the value, the magnitude was 2,400. The angle was 30 degrees, sine of 30. Let's plug it in and see what we get. So 2,400 times the sine of 30 degrees, which is equal to 1200. From the calculator, we can say that this is 1200 newtons down. Now let's look at the horizontal component. We're going to say it's 2400 times cos of 30 degrees. Now, it's not going to be the same angle, so let's make sure that we work carefully. We're going to say 2400 times the cos of 30 degrees, and that's equal to 2078,46. 2078,46. 2078,46. Which direction is it? Take a look. It's definitely going in that direction, so that's to the right. how are we going to deal with these directions? An easy way is for us to give a sign convention. When we say left and right, up and down, we'll deal with all those things that are horizontal and all those things that are vertical. What we're going to say and define is that to the left is going to be negative, to the right is going to be positive. We'll also say that up will be positive and down will be negative. Now, you can change that convention, but that's the one that we're adopting now. Now, we've done two forces. We resolved two forces into their components. What about the third force? The force of the earth pulling down on the load. Well, have a look carefully at it. We recognize it directly downwards. So it only has a vertical force. So what we need to recognize is that this is a part of those that are vertical. So let's take all the vertical components now, and we're going to say vertical components, and we're going to add them. And we're going to say FG is the first one, plus the vertical component of the rope, plus the vertical component of the cable. And I think I had that in another color, so let me just put that plus vertical component of the cable. It's interesting that you can label them so that the person that's following you can see exactly what you're getting at. And so here what we're going to do is we're going to add these numbers together. 5145, 5145, the rope, the vertical component of the rope, which was the one that I did in pink, the vertical component was 1200 down. Notice that these are both plus because they, or we should say they're minus because they're down. So let's get our sign convention. We're going to add in the next one, which is the cable. And it was 388909. And we're going to just write that down. 388909. And notice that I'm putting this as a plus because it's up. So what I can now do is I can use my calculator to add all of these components, these vertical components together to give me one big vertical component. I hope you can see where this is going. So let's do that. Let's put it in minus 5145 plus minus 1200, and then my last figure was plus 3889,09. And what I get is an answer of minus 2455,91. So I'm going to write that down as my overall vertical, minus 245591. So equals minus 245591, and that is in newtons. And we can remember to say that that is 245591 newtons down. So we've got that part sorted. Now what about the horizontals? Let's get those done. We recognize that there we only have to add 2 because the vertical, the force due to gravity didn't have. So the horizontal components, we've got the horizontal component of the rope and we've got the horizontal component of the cable. And if we look at the first one, which was the cable, we recognize that that was the same value as the vertical component because it was at 45 degrees. So it's 388,909. So that's the cable plus 388,909. And what about the rope? The rope was a different value. It was 207946. 207846. 207846. But guys, these were in the opposite direction. We need to apply our sine rule here. And we said anything that goes to the right is positive. So the rope was to the right, but the cable was to the left. So have a look and see what the answer is. Now, I'm sure you can see that it's going to be to the left as our final answer. Let's do the calculation. We're going to say 2078,46, and we're going to subtract from that 3889,09. That gives us a negative answer, meaning to the left of 1810 minus 1810, and the decimal place there was 0.63. So let's fill that in, 63. This means that it's 1810,63 newtons to the left. So all that remains now is that what we recognize is that we've got a horizontal component and we've got a vertical component. We've added the sum of the vertical components and we've got that number, and we've added the horizontal components and we get that number. So in effect, what we've broken down to is a horizontal component to the left and another one, which is this one, vertically downwards. So that's your vertical and that's your horizontal. This one was 18063 and the vertical one was this number here, which is 24, all added together, 245591. 245591. So we're not finished yet. How are we going to find the resultant? Well, I hope you can see that what we're going to do is we're going to add these together. We've got to change them and make them head to tail. And if I do that, and I move this one, I want to move it horizontally, move it down to there, get it into a position that it's at 90 degrees, then my resultant vector force is going to be in that direction. How am I going to find this F resultant? I'm going to use Pythagoras, and I'm going to calculate that angle using the opposite over the adjacent. Okay, now you can see we've done a process like that previously, so I'm not going to do it again, but I want you to make sure that you work through it so that you get the right answer. We'll just confirm the answer, but I think it's about time now that you had a little break and make sure that you've got everything sorted. Welcome back. That problem was quite tough. Let's just go over the final solution. While you were in the break, I worked it through. So we had our vertical components, summed those, and we got this number, 245591. We summed our horizontal components, 181073. Then we drew a sketch, and then I said you're going to use Pythagoras. And here's my calculation. So using Pythagoras and then taking the square root, I got the magnitude to be 3051,21 newtons. Use tan theta, and I've got 36,4 degrees. So the resultant is 3051,21 newtons at an angle of 36,40 degrees, and that's to the vertical. So we must make sure that we say to the vertical. Okay, so hope you can see that we can put these things together. It's really quite straightforward. If we know components and we know Pythagoras and tan theta, we can solve any problem. It's the same procedure every time. Whether you've got 2, 3, or 4, it would be a bit lousy to give you 4, but it is possible to do it in exactly the same way. Okay, let's move on. There is a final little concept that I want to deal with, and we've mentioned it already, the different types of forces that we get. And the ones that we are particularly interested in are the force of friction and the normal force, because they're related to each other. So then when we talk about friction, remember, it's the thing that opposes another force or opposes motion. So if you've got, it opposes the beginning of movement, even if you opposes an applied force, And if the object is moving, then the force will be opposing it. And so for that reason, there are two types of frictional force that we'll come to. And the one we'll talk about is static friction, and the other is when there is an object in motion, and we'll call that kinetic. Kinetic because of motion. Now, the normal force is a force at 90 degrees to any surface. And we will look at that and make sure that we've got that. It is related to the force of friction. So we need to know how to work those together. So let's have a look at static friction first of all. Here is the equation for static friction. We'll say static friction, the maximum static friction can be, is equal to something called the coefficient of static friction times the normal force. So the coefficient of friction depends on the surface that the objects are interacting with. And so if it's stationary and we start to push, then there's a coefficient, there's a value that we call the coefficient of friction that will give us an indication of those materials as they interact, how strong that frictional force will be. In a similar way, we define kinetic friction as Fk is equal to nu k times Fn, and the definitions stay the same. So please bear in mind that the static friction will always exceed the kinetic friction. Let's just have a look at a demonstration to show this. And so I'm going to refer to something on the web. It's a simulation from PhET. Really great guys. They've put together all sorts of physics demonstrations. We're going to look at pushing some objects. Now, I know that in this case, just so that you can see it, we'll put up the website as well. We can choose different objects, and you can change the coefficient of static friction, the coefficient of kinetic friction as well. So in this case, what I've got is I've got an object, a cupboard, and I want to be able to get my keyboard out. So let me get the keyboard and make sure that I can use this to fill in some values here. What I need to do is I need to fill in the applied force. So what shall we start with? We're told that the cupboard has a mass of 200 grams. I'm going to suggest that we fill in a force of 200 newtons, just to give us a go. And we'll press the go. And what I want you to see, and this is the important part, not so much the numbers. We've put in 200. I know that was very small, but have a look at the blue and the red arrows. The frictional force is equal to the applied force. The object is not moving. Let's increase the size of the frictional force. Let's make it 400. And let's see if we can get that to go. And again, even though we've doubled the force applied, the blue force and the red force are equal. It's not going anywhere. The more we push, the more the frictional force acts against us. And they're balancing each other up. So the object is in equilibrium. There is no change in its position. Let's try another one. I'm going to try 800. And let's see what happens. There we go. Now you can see the applied force is bigger than the frictional force, and the object, the cupboard, starts to move, and it gets quicker and quicker as it moves. Let's just have a look at that again. We can see that the applied force is bigger than the frictional force, and there is a resultant. And there we go. We see the object moving again as it moves from left to right across the screen. So what's happening when it's stationary is the application of static friction. Once we overcome this barrier and it starts moving, then we've got kinetic friction. And the formula, the values might be a little different. We need to recognize that static friction will always be bigger than kinetic friction, because once it starts moving, it's not so difficult to carry on pushing. So let's go back and let's see if there's some examples that we can deal with for this particular section. So the first one we're going to come to is similar to the demonstration I've just given to you. It says to you, what is the minimum force? What is the minimum force required to move a cupboard with a mass of 430 kilograms that is resting on a carpet. The coefficient of static friction for this situation, for these surfaces, is where nu is equal to 0.56. That's quite a high coefficient of friction, but we need to make sure that we've got it. So let's just draw a little sketch so we've got it clear. Here is our cupboard, and we know that the mass of the cupboard is equal to 430 kilograms, and we know that acting on that object, if we look at all the forces acting on, there is Fg and there is the normal force. Now, because it's stationary and because those are opposite each other, we know that the magnitudes are equal. So let's work out what Fg is going to be. We're going to say it's the mass times the acceleration due to gravity, 430 times 9.8. Get the calculator up and do that. 430 times 9.8, and it's 4,214. 4,214 newtons. That's the force of gravity downwards. What we need to recognize is the normal force is 4,214 newtons up. Excellent. So how are we going to find the frictional force, the minimum frictional force? Well, the equation we were given was the frictional force is equal to nu static times the normal force. So we've got the nu value. It's just a Greek letter, 0.56. It's a constant. It varies for different surfaces. We're going to multiply that by the value of the normal force, 4,214. There we go. And let's put it in, 4,214 multiplied by the coefficient of friction, which is static friction in this case, 0.56. And we get an answer for the frictional force. The frictional force of 2,359 units, 84. So it's 2,359,84. 2,359,84 newtons. Right, I think that's about it. We've done a lot today and covered a lot of detail about forces, different types of forces, different methods for finding forces. I wish you all the best as you further your studies with this section of mechanics.